Hello and welcome to another video for pre-calculus. In this video, we are going to discuss about logarithmic functions. So now in the previous video, we discussed about the exponential function, and the first example that we took was y equals 2 to the x. And remember, if we have to find the inverse of this function, we do switch x and y. So x equals 2 to the y. So this is the inverse of that function. Now let's go ahead and graph this function, okay? We'll make which is right here, we'll make a table and then graph. So now you have to be a little bit careful here. If we pick a value for x, it might be challenging to solve for y. So what we are going to do here is we'll do the opposite. We'll pick values for y and then we'll find x. That way it's easy, okay? So I'm going to pick some negative and some positive values. So if I pick y equals negative 3, then x equals 2 to the negative 3 or 1 over 2 cubed, which is 1/8. Now if I pick y equals negative 2, then I get x equals 1/4. And then if I pick y equals negative 1, I get x equals 1/2. Similarly, if I pick y equals 0, I get x equals 1. Y equals 1, x equals 2. Y equals 2, x equals 4, and so on. Now let's go ahead and graph this one. So one thing that we notice from here is no matter how smaller you make y in the negative or how large you make y here in the positive, x is never going to be 0. So it's something that we need to pay attention here. Okay, so when x is let's start from here. Okay, so when x is 1, y is 0. So when x is 1, y is 0, means it's right here. Now let's move up here. So when x is 1/2, y is negative 1. So when x is 1/2, y is negative 1. So it's down here. And then it gets closer and closer to that y-axis. So 1/4 and then 1/8. So it gets closer and closer to y-axis, okay? Now when we move on the right, when x is 2, y is 1. When x is 4, y is 2, and so on. So the graph looks something like this. That goes forever in this direction and forever in this direction. Now, I said earlier, this graph is the graph, the inverse of the y equals 2 to the x. So if we already graphed that in the previous video, y equals 2 to the x, which is a graph right here, like this, going this way through 4 and that way. Now, we know that the graph of a function or any relation in its inverse should be the reflection on y equals x, this line, okay? So the blue one is x equals 2 to the y. The pink one that I have here is y equals 2 to the x. So this blue line is the inverse of the pink line, or this is the inverse function of that one. Now the question here is, when we find the inverse function, we want to write the inverse as explicitly y equals a function of x. But now the problem that we have is we have x equals 2 to the y. Now how do we solve for y? It's in the exponent. We cannot do this just with ordinary math. We cannot take root y. If I take y root and then I have y here, so I really cannot solve for y, okay? Now, in order to solve for y, or in order to write that as a y as a function, explicitly function of x, what I need to do is we'll define a new type of function that is called the logarithmic function. So here's the formal definition. When we have y equals log base a of x, which we read that way, y equals log base a of x, then this is equivalent to, or this is same as writing x equals a to the y. So when we write y equals log base a of x, so this is same as writing x equals a to the y. So now to solve for y, we have to write it this way: y equals log base a of x. So this function is called the logarithmic function. So there's some restriction here. The first restriction is x should be always positive, not even zero, no negative and not even zero. So this x is always positive, or whatever the quantity inside the log, okay, this quantity must be positive. And a is a positive constant other than 1. So a cannot be 1, okay? It has to be other than 1. So some those are the two conditions that we need to pay attention to, okay? Now, what does that mean? So what does that log actually mean? So let's go ahead and find this one by hand, and then that really helps us to understand what that log means, okay? Now log base 10 of this number here, which is 100,000, equals what? That's what we want to find. So the meaning is, if we write that again, so log base a of x, so y equals that one, means that just mean x equals a to the y, or what power of a equals x. So here, what power of 10, okay, so what power of 10 gives us this number, 100,000. So that is the value of this log. So 10 raised to what power gives us this one. So we know that 10 raised to 5 gives us 100,000. So log base 10 of 100,000 is 5. Similarly here, this meaning of this log equals what? Okay, what here? This box means 10 raised to some number gives us 0.00001. And we know that 10 raised to negative 5 gives us this number. Okay. Now similarly, same thing here. This equals what? Which means 2 raised to what power gives us 16. So we know that 2 raised to 4 gives us 16. That means log base 2 of 16 is 4, this number. Okay, so same thing here. 25 raised to what power gives us 5. We know that the square root of 25 equals 5, and square root of 25 is same as writing 25 to the 1 half. So 25 to the 1 half gives us 5. That means log base 25 of 5 equals 1 half. So that is the meaning of log, which is just comes from here, okay, from this the definition. Now a few things that we need to note. The first one is log base a of 1. No matter what base we have, the log of 1 is always 0, and it comes from here. So log base a of 1 equals 0 means a raised to what power equals 1, so it is 0. Any number raised to 0 equals 1. That's why this is 0. Similarly, log base a of a. If this base and this number are same, then the value of log is 1. It also gives the comes straightforward from the definition, because a raised to what power equals a, which is 1. That's why this is 1. Okay. Now this might be very important tool that we need when we change from logarithmic to exponential and exponential to logarithmic. So we can always express a logarithmic function in an exponential form. Okay, so this is what helps us to do that. So log base a of x equals y is same as writing x equals a to the y, or we can go from here to here or here to here. Both are equivalent. Now I have an easy trick to write this one. So this is what I do. If I have to change the log into exponential, always the base is same for both. So the base for log is a, base for exponential is also a. Okay, now this is what I do. I start with the base, we go to the other side, and we come back here. Okay, so a raised to the power of y equals x. Now, this is an exponential. If I have to write the log for that, I do the same thing. I start with the word log, then this base is the base for log, and then I go around. Okay, so log base a of this number x equals this number y. So this is how we change from log to exponential and exponential to log. Let's look at some examples. So the first one here, we need to change this one to logarithmic equation. Okay, what is the meaning of this one? So 2 raised to what power equals 32. That's what this is. Now when we write that in terms of log, always if we are using this one, so log base a of x equals y. So if you are changing that into the exponential, a to the y equals x, or going from here to here or here to here, either way, what we do is we always write that log or exponential to the left, and then we can just go around. Okay, so I will write this one as 2 raised to x equals 32. Now I just do this. So this is the base, and we go to the next number right here, and then we come back here. So we write log, so this is I'm just writing log base 2 of 32 equals x. Okay, so that's how we change this one. Now similarly here, we already have that exponent to the left, so we'll start from here, we'll go to the other side, and then we come back here. So this means log base 10 of this number equals -4. Similarly, the last one, we start from the base, so log base e of, we go to the other side, 65 equals x. So that's how we change from exponential to log. Okay, let's do the other way. So in the next example here, we have the logarithmic equation. We are going to change them to an exponential. Okay, so again, we start with the base. So this is equivalent to 2 to the fourth equals 16. So this is exponential equation. Again, we start from a, we go to the other side, and we come back here. So a raised to the power of 7 equals m. Now here again, if we want to do that, let's put this one in the left hand side. So we can write log base b of q equals x, and that is we start from the base b raised to x equals q, so we go around. Okay, so equals q. So these are the exponential equations which are equivalent to the given logarithmic equations. Now there are two important log with two important bases, okay, that we use a lot. The first one is called common logarithm, okay, so which means the log with base 10, so common log. So this one we don't write base. So if you see something that just has log of a number here, okay, that means we have to understand the base is 10, because we don't write base for log 10. It is common, is self-understood. Okay, so log of m means the base is 10. So from now onwards, we are not going to write that base. Similarly, there's another log which is very important. We use this a lot, so which is called natural log. Okay, so with the base e. So if we write L and M, or this means ln means log with base e. Now just writing log means this is log with base 10. So if we write ln, we have to understand it's a log with base e. We don't write it log base e. We just write ln. Okay, natural log. Now in your calculator, you'll find these two keys in your calculator. So you'll find ln and log written in your log. So they are just next to each other. I think log comes first, and then natural log of the log with base 10, or the common log, and then natural log. Okay, so we can find this in the calculator. we can use this to evaluate the log and natural log of some numbers. Okay, so let's look at some examples here. So let's go ahead and use the calculator. Again, in the calculator, first what you have to do is hit log key. When you do that, if you hit that in the screen, you'll see log and then parentheses like this. Then you have to put that number 2, 3, 4, 5, close it and enter. When you do that, then that gives us the value for that log, which is if you put that in your calculator, you'll get 3.3701. Okay. Similarly, you can put this in your calculator log and 10, but we know that this is log means base 10, and we have 10 here. If they match, then this must be 1. We can do that without using the calculator, but you can put it into the calculator as well. Now this one is not possible. Probably your calculator will say error because remember for the log, this inside number, this cannot be negative. So when we write log x, x must be greater than 0. So it has to be positive number. So again, in the calculator, just below log, you'll see a key that has ln. So that's what you hit to find the natural log. So when you hit that, your calculator will the screen the in the home screen you'll see ln and then parenthesis. Then if you put letter e and close it and enter, then it gives you the value. So natural log of e is 1. Again, why? Because natural log means log with base e, and if we have e here, if they match, that should be 1. That's why natural log of e is 1. Now natural log of 27, again, if you put that into the calculator, you get 3.2958. Okay, so that's what you get from the calculator. Now let's look at the graph of this log function. So before we graph it, let's go ahead and find the domain, range, and the asymptote, and then we'll graph. Okay. So the first thing, domain, we know that x cannot be negative, or the quantity inside that log function cannot be negative. So x must be positive. So this is the domain, okay? And in interval notation, we can write this one as 0 to infinity. Now the range is all real numbers. So this can be written as negative infinity to infinity. Now remember, we said that the exponential function and logarithmic function, they are inverse of each other. If you remember from the previous video, the range of the exponential function was this one. So range of exponential, okay? And this was the domain of exponential function. Remember, for the inverse, we just switch range and domain. So that's what's happening here, okay? Now the vertical asymptote is always this x equals this number right here, or x equals this number. So vertical asymptote means that's the vertical line. The graph cannot cross that line. So when graph approaches closer and closer to that line, the graph goes to the negative or positive infinity. Okay. So the vertical asymptote here is x equals 0. Okay, so with the exponential function, we have the horizontal asymptote. For the logarithmic function, we have the vertical asymptote. So let's go ahead and graph this one. So vertical asymptote is x equals 0, which means the y-axis. So this is the vertical asymptote. Okay, now to graph, we need at least 2 points. That's all we need. Okay, now think about this one. Okay, when does this log become 0? So if you think, when does log of x becomes 0? It becomes 0 when x is 1. Remember, log of 1. We just looked at it right here. Here, log of, no, not here. Log of 1 is 0. So we just looked over here. Okay, so now using that, we know that log of 1 is 0. So when x is 1, the y value is 0. So when x is 1, the y value is 0. So it's right here. And then when does this become 1? When does that log becomes 1? So log, this log means it has a base of 10 of x. So when x is 10, they match and it becomes 1, right? So log of log base 10 of 10 is 1. So that means when it is 10, it is 1 here. So this goes to the negative infinity because we have that vertical asymptote, and then the graph goes this way, and then that's how the graph of log of x looks like. Okay, now let's look at this second one here. This is just the transform form of that one. So if you just look here, we added 2 to the x. That means the graph will shift to the left 2 units. So you can say that just looking using the transformation. But let's go ahead and find the domain. So now here the domain means this quantity inside the parentheses cannot be negative or 0. So it has to be positive. So this is how we find the domain. To find domain, we say x plus 2 must be positive, which means x is greater than negative 2. So that is the domain. Now if you write that in interval notation, we write negative 2 to infinity is the domain. Now the range, again for logarithmic function, range is always all real numbers. We really don't worry about the range. Now the vertical asymptote, again I said that vertical asymptote is x equals this number or this number here. Okay, so x equals negative 2 is the vertical asymptote. So let's go ahead and draw the vertical asymptote first, which is right here. This is the vertical asymptote. Now in order to graph this function, let's see. So we have log of x plus 2. So we need to find at least two points, okay? So the first one, when does this become 0? Whenever this inside quantity is 1, because remember log of 1 is 0. So when does this inside quantity becomes 1 is when x is negative 1. So when x is negative 1, we get log of 1, which is 0. So that means the x-intercept is right here, okay? Now, when does this become 1? So this becomes 1 if log this inside quantity is 10. We have x plus 2, so the inside quantity becomes 10 when we have x equals 8. So it's right here. This is where it's going to become 1. Now we know that it has a vertical asymptote, so from here it goes closer and closer to that line and goes to negative infinity. And then the graph goes this way to the right. That's how we graph this function. Okay, so let's look at more example here on graphing. So the natural log of x. So let's look at the graph of this function. Now, before that, let's go ahead and find the domain. Again, it's a log, so domain means x is greater than 0 or negative, sorry, or this means 0 to infinity. So that's the domain. Again, range, all real numbers. Now, vertical asymptote, x equals 0. Now to graph, again, we need to find 2 points. So what we have is we have natural log of x. So when does this become 0? Whenever x is 1. So it's 0 right here. And let's go ahead and graph the vertical asymptote. Sorry, we should do that first. So this is the vertical asymptote, which is x equals 0. Now we got 1 point, so we just need one more point. Now, when does this become 1? So it becomes 1 whenever x is e, because we have same, the base and the number are same when x is e. E means 2.718, so it's close to 3. When x is close to 3, that becomes 1, so it's somewhere here. Okay, now again, it goes to negative infinity, and then it goes this way. So that's how the graph is going to look like. Okay, again, we can graph this in the calculator, but we're just trying to do this by hand just to see how the graphs looks like and just to understand the transformation. Okay, so now here the transformation is we are subtracting 2 from x, so this is moved to the right 2 units, so right 2 units, and then we are adding 2, so up 2 units. So that is the transformation. Okay, that might help us to graph this function. Now, before that, before graphing it, let's go ahead and find the domain, range, and the asymptote. So domain is whenever this inside quantity is positive. So for the domain, we have to do x minus 2 greater than 0. that gives us x is greater than 2, or in interval notation that is 2 to 0. Okay, so that means the vertical asymptote. So before that, let's write range, all real numbers, we don't have to worry. Now the vertical asymptote here is x equals 2. So that means the vertical asymptote is right here. Basically, in order to graph that one, we can just use this graph right here and just do the transformation. We can just move to the right and up and then graph it if you want. So for example, the point 1, from here it should go 1, 2, and up 1, 2. So that point right, this point should go over here in this one. It should go over here, right here. Okay. And similarly, this point right here should go 2 to the right and 2 above. So that point, so this point here, 2 points, so that point should go 2 to the right and then above, it should go up. So it should be somewhere here. Okay. Or in another way, we can just look over here. So ln x minus 2 plus 2. So when x is 3, we get 3 minus 2 is 1, so this becomes 0, we get 2. So when x is 3, y is 2, the first type. Now the second is this becomes, so when x is, let's say 4 point something, 4.17 or something, now that this becomes e, so that means this becomes 1 plus 2 is 3. So when x is 4.718, then it becomes 3 here. So this is how the graph of this function will look like. Okay, so let's look at one more graphing and then we'll be done. So here, this is a log with base 2. Again, it doesn't matter what base we have, the domain means this quantity must be positive, something that's inside that log, okay, inside the parentheses. So for domain x greater than 0, which means in the interval notation it is, why do I write negative? So 0 to infinity, okay. Range, always all real numbers. Vertical asymptote, we'll just look over here. So x equals 0. That's the vertical asymptote. Now we'll go ahead and draw the vertical asymptote first. So x equals 0, it's right here, the y-axis. And then, now this graph is shifted up 2 units from the original function log base 2 of x. Okay, we have plus 2, so it's moved up. But when we are graphing, we can just check this way, okay? So we have log, what we have is we have log base 2 of x plus 2, okay? Now when x is 1, the whole quantity becomes 0, so that means the y value is 2. So when x is 1, y value is 2 right here. It's just moved up, okay? This 2 was not there, it would be at on the x-axis, y is 0, but it's moved up 2, so that's why we have at 2. Now when x is 2, we have log 2, log base 2 of 2, which means this quantity is 1, but plus 2 is there, so that becomes 3. So when x is 2, it is 3. So again, we can just draw this graph like this. We don't have to draw perfect. That's what we guess it looks like. Okay. Now this one, this is the graph of log 2 shifted to the left 2 units. Okay. First, let's go ahead and find the domain. Domain is x plus 2 greater than 0, or in when we solve it, we write x is greater than negative 2, or in interval notation, negative 2 to infinity. Now, range, all real numbers, nothing changes. Then the vertical asymptote is x equals negative 2. Now, let's go ahead and graph the vertical asymptote first. So, x equals negative 2 is the vertical asymptote. Now to graph, let's look over here. So the function that we have is log base 2 of x plus 2. Now when does this become 0? So this becomes 0 when this inside quantity is 1. When does the inside quantity becomes 1? Whenever x is negative 1. So we have 0 right here. Sorry. We have 0 right here. Now, when does this become 1? So whenever the inside quantity is 2. When does the inside quantity becomes 2? Whenever x is 0. It's right here. Again, this graph looks something like this. We're not going to draw the perfect, but that's what we guess. Okay, that's how we do this by hand. You can check this using a calculator. That's all we'll do in this video. In the next video, we'll continue with more exponential and log functions. Okay.